Hey everyone, welcome. In this explainer, we're going to dive deep and visually map out the core pathophysiology behind some really key childhood blood disorders. The whole point here is to get to the why behind each condition, so you can build this clear mental picture that's going to stick with you, especially for your exams. So here's our game plan for today. We're going to start with the amazing transition a baby's blood makes, from fetus to child. Then we'll jump into what happens when things go sideways. We'll look at iron deficiency, a really wild maternal-fetal conflict, the crisis of sickle cell, and the broken chain reaction in hemophilia. And at the end, we'll tie it all together so you can see the bigger picture. Okay, first things first, before we can really get what's going wrong in these diseases, we've got to get a handle on the just incredible changes our blood goes through from the moment we're conceived to when we're running around as kids. It's our baseline. Okay, so this is where it gets really cool. The design difference between fetal and adult hemoglobin is just genius. Fetal hemoglobin, or HbF, has this ridiculously strong grip on oxygen. And why does that matter? Well, it allows the fetus to literally rip oxygen away from the mother's blood, right across the placenta. But once the baby's born, the whole game changes. We switch over to adult hemoglobin, HbA, which has a much looser grip. That makes it perfect for its new job, dropping off oxygen to all the body's tissues. This whole switch is a huge plot point in the diseases we're about to cover. So what happens when the body just doesn't have the right building blocks? Well, that brings us right to our first disorder, iron deficiency anemia. And this one, it isn't about the genetic lottery. It's something you acquire, and it unfolds in a really clear step-by-step way. And you can literally see the dominoes fall right here. It all starts with a simple supply problem, not enough iron coming in. So the body does what it can, it starts raiding its own iron savings account. But once that's empty, the hemoglobin factory just grinds to a halt. And the results? The red blood cells that do get made are small and pale. We call them microcytic and hypochromic. This means less oxygen is getting delivered everywhere, and that leads directly to those classic signs like fatigue and being pale. It's a perfect chain reaction. All right, let's switch gears a bit. We're moving from something you get to something you inherit. Hemolytic disease of the fetus and newborn, or HDFN, is a pretty dramatic story about what happens when a mother's and baby's blood types are basically at war with each other. Yeah, that big word, alloimmune, just think of it as friendly fire. The mother's immune system, which is supposed to be the ultimate protector, makes a huge mistake. It sees the baby's red blood cells as foreign invaders, so it sends out these tiny little antibody soldiers, IgG antibodies, that are small enough to sneak across the placenta and just start attacking the baby's cells. It's a full-on assault. Okay, so this breaks down the whole timeline perfectly. It all kicks off during the first pregnancy. You have an Rh-negative mom with an Rh-positive baby, and during delivery, some of their blood can mix. This sensitizes her immune system, which then starts building an army of anti-Rh antibodies. And you know what? That first baby is perfectly fine. The real trouble starts with the next pregnancy if that baby is also Rh positive. Now, that antibody army is pre-made and ready to go. They cross the placenta and just unleash on the baby's red blood cells. This causes massive destruction, leading to severe anemia and this dangerous buildup of a waste product called bilirubin, which we call hyperbilirubinemia. So we've gone from the immune system, but now we're going to go even deeper, like all the way down to the DNA itself. This is sickle cell disease, and it's just a wild example of how one tiny little error in our genetic code can have absolutely massive, devastating consequences. I mean, just look at this. It's kind of mind-blowing that this is where it all begins. One single letter change in the DNA for one of the hemoglobin genes. This tiny typo swaps out one amino acid for another, and that tiny swap creates a completely new unstable protein, hemoglobin S. This is it. This is the molecular ground zero for the entire disease. And this is what happens because of that one little change. You see these nice, round, squishy discs? Those are normal red blood cells. They're flexible and can glide through even the tiniest blood vessels. And then you've got these rigid, crescent-shaped, sickled cells. Their weird shape isn't just a cosmetic thing. It fundamentally changes what they do. They go from being oxygen carriers to being dangerous, rigid roadblocks. Okay, so how does this actually cause a crisis? What's the trigger? Well, it can be something like low oxygen or dehydration. This makes those faulty hemoglobin S molecules inside the cell start linking up, kind of like Lego bricks, forming these long, stiff rods. These rods then warp the entire cell into that sickle shape. And because they're not flexible anymore, they can't squeeze through the small capillaries. They create this massive traffic jam, a log jam. That's what we call vaso-occlusion. The blockage cuts off blood flow, starving tissues of oxygen. That's ischemia. And that causes just excruciating pain. Okay, so up until now, we've been all about the red blood cells, right? But what happens when the cells are fine, but the system that's supposed to keep them in the blood vessels is broken? Well, that brings us to hemophilia. And here, the problem is a breakdown in that vital clotting cascade. So you've got hemophilia A and B. And on the outside, they look pretty much the same. But the root cause? Totally different. Hemophilia A is from a missing factor 8, while hemophilia B is a missing factor 9. They're different pieces of the puzzle, but because they work in the same sequence, missing either one breaks the chain in exactly the same way. This is such a great way to picture what's happening. Normally, when you get a cut, there's this amazing, complex domino effect where all these clotting factors activate one after another. But with hemophilia, boom, you hit a brick wall. The cascade just stops dead because factor 8 or 9 isn't there to do its job. And without that whole cascade finishing, you can't form a strong, stable clot. The whole system just fails, and the bleeding keeps going. All right, let's pull all these threads together. We've looked at a bunch of different diseases, but if you look closely, you can group them into a few core mechanisms. And trust me, thinking about it like this, it's going to be a game changer for your exams. The big takeaway here is all about seeing the patterns. Each disease has a different root why. Like iron deficiency, that's a supply chain problem. You're just missing the raw materials. Sickle cell, that's a typo in the DNA instruction manual. HDFN was a case of mistaken identity, an immune system civil war. And hemophilia was a broken assembly line. A critical protein is just missing. When you can categorize the why, it gives you this powerful framework to understand the what and how of pretty much any disease. So I want to leave you with this question, because moving beyond just memorizing symptoms, really getting the fundamental mechanism, the pathophysiology, that's what separates just knowing facts from having real clinical insight. It shapes everything we do, from diagnosis to treatment to how we talk to patients. It's literally the foundation for everything.